Hey, year 12s, thanks for coming along, guys. Okay, so today we're finishing off our week into molecular forces. We're finishing off our WIMPs today with our final WIMP and the weakest of all the WIMPs, which is van der Waals forces, or otherwise known as... today with our final WIMP sorry, which is... there we go, sorry. Van der Waals forces, or otherwise known as London dispersion forces. There are two different names. Both names are accepted at Edexcel. If you're an AQA student who's watching this video, they prefer van der Waals. If you're an Edexcel student, then they prefer London dispersion forces. That's me being an exam prep teacher rather than a chemistry teacher. Either one, they are both accepted on both. It's just whether or not they sit in the accept column or the major column of the mark scheme, that's all. Okay, so we're moving on to LDFs and VDWs. I'm going to switch my camera over to my clip cam. Thanks, Harry. I'm always going to say thank you to that one, Harry. It's amazing. Woo! Right. Let's crack on. Okay, so I think we're good to go. I'll pop out the chat. Can I just ask all of my year 12s who are currently watching my video, which is all of 4, can I ask you guys, please, to just say hello on the chat, just so I know you're there. Okay, so today we're focusing on the final one of our WIMPs. So far, just to give you it in context, the WIMPs, weak intermolecular forces, we have so far done DDs. Those are done. Those are dipole attractions. We have also done HBs, tick, and we're now moving on to LDFs. Now, I'm going to focus, thanks, Harry, London dispersion forces. I'm using that term just because Edexcel prefer that term. You can also call them van der Waals forces, VDWs, if you like. It makes no difference what name you call them. They will be accepted on either one. But like I said, Edexcel, I'm going to focus on London dispersion. So 3 learning objectives today. We've got understand the origins of London dispersion forces, be able to describe it. So this is what you're going to have to learn for your exam. They're going to ask you for this description. So that one is really important. And the last one is understand why they build up. VDWs or LDFs, London dispersion forces, are cumulative. They build up with size of molecule. So it's a rather difficult thing, really, because when I teach this, one of the things I'm always saying is that hydrogen bonds are the strongest, and then dipole attractions. Notice the change in word. It's subtle, but it's there. A hydrogen bond, a dipole attraction, and then a force, a London dispersion force. So we're going from a bond to an attraction to a force. They're decreasing in size. So we know that LDFs are the weakest, but in reality, it's a bit more complicated than that, because LDFs, London dispersion forces, are cumulative because of their origins. Okay, so let's start breaking down London dispersion forces. So we understand so far, I think most people at this stage tend to kind of start to get a grasp onto what's happening here. In chemistry is fundamentally built from one force, and that is the electrostatic attraction. This force dominates everything through chemistry. Yeah, we know that, we can define an ionic bond as the electrostatic attraction between oppositely charged ions. It's electrostatic in nature. And then we can say covalent. And covalent, we would say it's the electrostatic attraction between the shared pair of electrons and the 2 positive nuclei of the two atoms. So that is electrostatic in nature as well. Then we drop to metallic, and we say it's the electrostatic attraction between the C of delocalized electrons, which is negative, and the positive lattice of cations. So it's also electrostatic in nature. And then we dropped into the WIMPs. And we realized that WIMPs are weak electrostatics. We realized that the dipoles are the electrostatic attraction between the slightly negative chlorine and the slightly positive hydrogen on adjacent molecules. It's electrostatic in nature once again. Then we drop into hydrogen bonds. Now, hydrogen bonds is the electrostatic attraction between the slightly negative fluorine, and I've got to show all lone pairs now, and the slightly positive hydrogen on the adjacent molecules, but it's attracted to the lone pair on the fluorine. the subtle differences, look at the subtle differences in these diagrams. The only difference is the lone pair, which is the extra bullet point in the description. Everything else follows. Yeah, so the 3 bullet point or the 4 bullet points. So this is chlorine, if I just do this really quickly, chlorine, higher electronegativity, higher En than hydrogen. Yeah, followed by permanent dipole, perm DD, followed by slightly positive hydrogen attracted to slightly negative chlorine. Yeah, and we're done. And then on adjacent molecules. And then we get hydrogen bonding, which is exactly the same thing. Fluorine, higher elec neg than hydrogen. So permanent dipole, it's nice to put it in, perm dipole, perm DD, and then we say slightly positive hydrogen attracted to the lone pair on the slightly negative fluorine. You're done. That's actually how you can do it. And the diagrams, the trick is in MD. Hello, can you suggest me where I can get help for IGCSE Excel human biology? Oh, blimey. No, I can't. Sorry, MD. I can't. There must be some YouTube stuff out there. Try having a look at what I'd probably recommend is, first of all, if you don't know about the website, I think Physics and Maths Tutor, does that have biology on it? I don't know if it does. Let me just quickly have a look. Just, sorry, since it's just kind of interjection there. If you do PMT on Google, I think there might be biology in there. I don't know whether or not it specifies into human. Yeah, biology is there. So if you go to the biology section there, you'll be able to see, and they'll be able to, so then you can go to Edexcel International. Yes, I think it does. Yeah, so I'd probably say start there with PMT. You can find notes, you see. So if you go to the International GCSE and you're doing Edexcel, so you could do paper 1 and you'll be able to find revision notes on there, I think, maybe, if you do revision, rather than revision courses. Let's see if I can track some of these down. There are notes on there. So if you go to revision, maybe, or IGCSE, if you hold your mouse over it, it usually pops up. There you go. And then you can go to biology and it should spit you up some notes. Ignore the courses bit. Just go onto the Physics and Maths Tutor website, hold your mouse over the GCSE bit, this will pop down, and then go to biology revision, and then you should be able to select for human biology. I hope you find that helpful. And you can have a look at some revision notes plus some exam style questions by topic. Hopefully be able to find human biology in there. Okay, so the only difference is the lone pairs. Now we're dropping into van der Waals forces. This is today's lesson, or London dispersion forces, LDFs. And once again, it's an electrostatic, but it's a rather interesting one. So the subtitle is London dispersion forces, LDFs, or sometimes known as van der Waals AA forces, VDWs. So either one doesn't matter. So, okay, so the question is, if we now understand, thank you very much, sir, no problem, MD. So if we understand that all of the attractions, all of the forces, all of the bonding in chemistry is based around the electrostatic, well, if you look at something like chlorine, chlorine has no dipole. It is a non-polar molecule. What that means is if it's non-polar, then there's no polarity. What that means is if you are going to have an attraction to another chlorine, we need to explain where this comes from, because there shouldn't be an attractive force, but we know there is. Now, students at this point often ask me, how do you know there's a force between them? The reason being is you can make them a liquid. If you can make something a liquid, there must be a force between the molecules that's holding them together. So we need to explain this and where this force is coming from. Okay, so van der Waals forces. First bullet point, let's do facts. Facts. Number 1, LDFs occur between non-polar molecules. So do you remember when we did polar bonds versus polar molecules? Yeah, it's the polar molecules that matter. So LDFs occur between non-polar molecules. So if I have a molecule which is non-polar, like methane, yeah, I am going to have an LDF, a London dispersion force. Now, can I actually just point out that it turns out LDFs occur between non-polar molecules. However, there's a rather odd thing. Number two, they also occur in polar molecules. Now, what that means is in reality, you can just simply say one sentence. And I'll do this in red. All covalent compounds, and you guys know that I mean simple, all covalent compounds exhibit LDF. All covalent compounds show LDFs. Now, this is really confusing for students because they're like, hang on a sec. So why did you bother giving us the first two? Because what this means is in this one here, it matters. Whereas in this one, it doesn't matter. Doesn't matter. The reason being is something else is going to be there, like a DD or a HB, which is way stronger than the LDF. So it doesn't really matter, so we tend not to consider it. There are exceptions to that rule, and I'll come to that. So in fact, what I want you to take away was that everything has LDFs. Now we need to explain what an LDF is. So how is it possible that hydrogen, a non-polar molecule, would be attracted to another hydrogen molecule? Okay, so here's the thing. Electrons aren't stationary. We know that electrons are permanently moving. We know that they actually teleport from one location to another. We can predict where they're going to be in orbitals based on Schrodinger's equations. You know about that. But we know that their electrons are always hopping about. They live in a space. So you remember when we covered orbitals, and we said in orbitals that there are three orbitals that you guys need to know about. The S sphere, the P, these are the ones you need to be able to draw. There you go. The PY, the PX, and the PZ. And what we realize is that the electrons live somewhere in this region. They could be anywhere within it, but they live somewhere in this region. They might live on the same side briefly. Yeah, but what they're doing is they're moving around inside this space. So what this means is we now get a fundamental bullet point here. So exam question number 1. Explain London dispersion forces. London dispersion forces. Okay, so the first thing we need to say, bullet point number 1, answer. Number 1, electrons are always in motion. Electrons are always moving. Number 1, tick. Let me explain what this means. It means that if I were to take a hydrogen molecule and I was to take a photograph of it, if I took a photograph of where the electrons existed, on any particular photograph, I might take a picture and see this. You realize that the electron cloud looks like this? Yeah, and you can see where the electrons are. And I've taken photo number 1, picture number 1. I'm now gonna take another photo. I take a click, snapshot, I'm done. I'm then gonna take a second photograph immediately after. Picture number 2. And we see this. The electrons have moved. Now this one hasn't moved much, but it has moved. But the other one has. So the electrons are in constant flux. We can go to picture number 3. Go to picture number 3. I should color code these really. Let's do this. Oh, I like that idea. Let's color code some electrons. I like that idea. So this guy's purple and this guy's orange. Right, I take the second photo. The purple guy is now here and the orange guy is now here. It has moved. Both of them have moved. I now take another photograph and the purple guy is now over here and the orange guy is now over here. Right, I'm going to take another photo and now I see this picture. what we realize is the electrons are constantly in motion. The purple guy moves to here, and the orange guy moves here. Now, because the electrons are in motion all the time, they're constantly hopping left and right. Yeah, they're constantly moving around. What you realize is there are always going to be times, there are going to be 50% of the time when the electrons are evenly distributed, and then another 50% of the time where it's not evenly distributed. So if we look at these four pictures, these ones are kind of opposite each other. So the polarity is now going to be said to be non-polar. But now, when the electron moved, the two electrons are living more on this side. I'm going to get a polarity. I'm going to get a slightly negative and a slightly positive here. In the next picture, the purple electron moves to the other side, and the polarity now disappears. It becomes non-polar again. But then in the next one, the electron jumps, and we end up seeing a polarity. This side is now slightly negative, and this side is now slightly positive. What this means is because the electrons move, this is the second bullet point number 2. The electrons are always moving. So you will, bullet point number 2, there will be temporary dipoles. So when the electrons, you don't need to explain why, when the electrons happen to be on a similar side, we're going to see a polarity. Now, the polarity isn't going to last very long because the electrons are going to repel each other and they'll hop to the other side and the polarity would be lost. But what we realize is there is, for a fraction of a second, a polar molecule, but it's only temporary, and we have to state that. Because the electrons are moving, there will be temporary dipoles. Now, what that means is if there's a temporary dipole, now here's the really cool bit. So if you now put molecules together, let's put a whole load of molecules together. Let's do these 3. And what we realize is if we do hydrogen and hydrogen again, yeah, what we realize is that the electrons are moving randomly. And I'm going to put these guys on orange and green. Right, I have a non-polar molecule there. They're evenly distributed. But in the next one, they hop to a different position. And this now creates a temporary dipole. This is now a temp dipole. Now that temporary dipole, if we look at the other guy doesn't have a dipole either. It happens to be that it's evenly distributed. But here's the really weird bit. When this one creates a temporary dipole, it has a knock-on effect. What will now happen is it will induce a dipole in the neighbors. Because we've got a slightly positive side over here, slightly positive, and over here a slightly negative, what happens is the electrons in the molecules now shift. Now this temporary dipole is still present. So we've still got this one momentarily. But what it's now going to do, I'll do them color-coded, yeah, what's now going to happen is that's going to now cause a dipole to become formed in the adjacent one. We know that this side, sorry, I've got those wrong way around. This side is slightly negative and this one is slightly positive because the electrons are on that side. Yeah, I'll stick with that routine. That one's slightly negative and this one's slightly positive. What now happens is the electrons on this side now immediately get repelled and they hop over to this side. Yeah, and what happens is it's inducing, that one will now form a dipole as well. This here is called induction. It causes a neighboring molecule to form a dipole. So because the electrons are moving, temporary dipoles will form. These dipoles, these temp dipoles induce, notice my capitalization, gotta have that word, induce dipoles in neighboring molecules, in, if you prefer, adjacent, the neighboring, partly because it's easier to spell, I'm with you on that one, dipole in adjacent molecules. And now there's going to be an attraction. Because if you form a dipole, there we go, we now have an attraction, a very weak attraction, between the slightly positive in the temporary as there was in the other. Now, this isn't going to last very long because the electrons are then going to move and the dipole will be lost. So the force is incredibly weak. But the great thing is the story is almost complete. Electrons are always moving. There will be temporary dipoles formed. I like the word formed. Formed. These temporary dipoles induce dipoles in adjacent molecules. Attraction between temporary dipoles. Temp dipoles. You're done. That's it. Those are your 4 board. There's your story. And guys, I'm so sorry that you have to learn these. And each of them does have a story. And they're each very apart, I mean, DDs and HBs are related. You just have to add in lone pairs. But VDWs is very special. Electrons are moving, form temporary dipoles. These induce dipoles in the neighboring, attraction between temporary dipoles. You're done. And so the next question is, why are they accumulative? So what we realize is that if you compare molecules, fluorine, chlorine, bromine, and iodine, these guys are the classic. These guys, fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. We can pick up a trend in boiling points, and the trend is increasing. As we move down the group, the boiling point, the BPT, is increasing. Well, the question is, why? Because there are no different forces. All of these, every single one of these is LDFs. There are no permanent dipoles. There are no hydrogen bonds. This is only LDFs, only London dispersion forces. So why would they be accumulative? The reason being is, if you look at the picture of electrons, fluorine has a grand total of each fluorine atom has 9 electrons. So it has a total of 18 electrons in its cloud. What that means is the chance of the distribution being even or not even are relatively small. If you then go to the larger molecule of chlorine, chlorine now has 17 times 2. Do you have a calculator? This now has 34 electrons. The chances of those electrons being evenly split across the length of the molecule are now getting relatively slim. So the forces increase. It's going to be more that the temporary dipoles will last longer and will be larger, because electrons do a rather odd thing. They kind of the description is slosh. I'm going to add, there's bromine. Bromine's even larger. Each bromine has 35 electrons, which means in that alone, there is 70 electrons now in this cloud. So, and then iodine, blimey, iodine's enormous. Yeah, iodine is element, I don't know, 126. No, it can't be that big. God, is iodine epically? Sir, my teacher says that one are overall stronger than permanent because the permanent dipoles have to be a specific orientation. Is that true? Oh, what a lovely question. You do know that's not a good description. Your teacher is correct. If you have, oh my God, no, it's not correct. We understand that there will be an orientation, and the orientation does matter, and it matters for reactivity, because for reactivity, the orientation matters. But in terms of forces, that's not true, because the molecules will immediately orientate themselves. Have you ever played with a magnet? Have you ever got two bar magnets? By the way, iodine, 53, my bad, 53. If you ever take 2 bar magnets, that's a really odd thing to say. If you ever take 2 bar magnets, north and south, and you push them together, with the opposite directions, and you push them with one finger, yeah, and so you push them together, what you'll find is this one will immediately rotate. Either one will rotate. Whichever one rotates first will rotate. And once they rotate, they'll lock together it will swing around so that the orientation is now correct. Yeah, so no, that's not a good description there. North and south. No, it has nothing. Now you have the attraction between the two of them. No, it's that the orientation of molecules is more important for reactions, Epi. Sorry if you don't mind me calling you Epi. No, Van der Waals forces or London dispersion forces they're not. There are London forces that are weaker. Oh my God! If you like, you could go hydrogen. Yeah, this has 2 electrons in the molecule. The London force here is going to be insanely weaker than any DD. If you have a DD between HCl, I don't care whether or not they repel each other if they're the opposite way round or not. Yeah, that has nothing to do with it, because this one will just reorientate. It'll just swing, and so there is an attraction. You don't look at it as in saying that one is stronger. The only time that you ever say that the LDFs are stronger than DDs is when the molecule is large enough. And it's only done on a comparative epi. Your teacher is missing the exam style questions there. Because what they're going to do is they're going to do clever tricks. So, for example, in order to compare the WIMPs, in order to compare DDs, HBs, and LDFs, in order to compare them, you've got to make sure that there's equal comparison across the board for certain situations. So, for example, if you were going to compare chlorine, LDF. So this here is an LDF. We know that there is a London force. Yeah. And that force is going to be weak. But you cannot compare that to the HCl DDs. You can't do that. We know that there is a DD. That's a permanent dipole attraction. And that's an LDF. You cannot do that comparison. No. The reason being is because the chlorine molecules have an MR of 71 and the HCl molecules have an MR of 76.5. What that means is the larger size of the molecule means that it's going to have stronger LDFs. You cannot do that comparison. If you're going to compare the forces, you must make sure that something is equal. And most of the time, it's the LDFs. You can't really compare them directly. But what you know is that LDFs are the weakest. But we also know that they are cumulative based on the size of the molecule. So, for example, a better comparison would be something like, got to be really careful here, blimey. A better comparison would be HCl has an MR of 36.5. And I'm going to compare that, got to be really careful here. I'm going to compare that with H2S, with that guy. Yeah, the reason why I do that is because they've got very, very, very similar MRs. That's 34 point, sulfur 32.1 plus 34.1. That these are incredibly similar MRs. Similar MR, so ... similar LDFs. Everyone has LDFs. Similar LDFs. So if there's similar LDFs, the only difference in boiling point would be between the DDs that are being formed. Neither of them show hydrogen bonding because they don't include the fun of hydrogen bonding. You need hydrogen bonded to fluorine, oxygen, and nitrogen directly. So these are only DDs. They're DDs and LDFs, but you'd never bother talking about the LDFs because they're weaker than the DDs in this scenario. So we now can compare the DDs, and I would expect that the HCl would have a higher boiling point. The reason being is the difference in electronegativity is 3.2 and 2.2. So the difference there is 1, whereas the sulfur is 3. So it's going to have a smaller difference. So the H2S will have, that's 3. I like to put chlorine as 3.5, it's easier, and 2.2. So that has a 0.8 difference. So I would expect HCl to have the higher boiling point because it has a bigger difference. And I'm going to ignore the LDFs because they're similar, because the molecule's MR is similar. And that's a key point. Nota bene. Nota bene at this point. 5, you need to really know this, guys. Nota bene. The bigger the MR, the bigger the MR, the stronger the LDFs, the London dispersion forces. Yeah, that's a super important nota bene. Cannot stress that. Okay, so let's now do some more comparisons. By the way, it'd be interesting to look at the difference, wasn't it? And check to see if my thing is correct. So HCl boiling point, let's go for that. HCl boiling point is minus 85.5 degrees Celsius. What's the boiling point of H2S? It should be lower. H2S. Boiling point minus 60. Oh, that's interesting. H2S, have I done something wrong there? Isn't that interesting? Oh, so that's minus 60. Whereas I would expect that one to have the higher. Breaks a rule. Isn't that interesting? Difference one. Huh. How fascinating. Breaks a rule. There's going to be something going on there. That's weird, that. Is that correct? No! Hang on a sec. Difference is point. Yeah, they're very, very similar. It's messy. I've given a really bad example there, guys. It broke a rule. It's awkward. Sorry about that. Let's try something else. Okay, we need to work with ones here that we're going to be getting. This is my point of the exam. You've got to, you've got to put this into exam style questions because you've got to be really careful with bonding because bonding always has an extra layer to it that's always coming, and there's always oddities in this, and that was a bad choice for me there, and I apologize for that. But let's look at ones that we know are going to work out. So if I said, let's compare the hydrogen group 7 molecules. So let's do HF versus HCl versus HBr. Let's compare these. Now, what we realize is straight off the bat, which one would you expect? So the first thing is, I think, you know what we need to do is identify the WIMP. So first of all, what WIMPs are occurring? So on the chat, please. Nice to see people contribute. On the chat, what WIMP are we seeing for HF? What WIMP are we seeing for HCl? And what for HBr? So you can pause the video, have a go at your answers, and then check them. So HF straight away is hydrogen bonding, HBs. HCl is DDs, and HBr is DDs. Now, the next thing to note is that they all include LDFs as well. Everybody has LDFs. But the thing is, we're not going to talk about them. We're not going to bother. The reason being is because there is a stronger WIMP there available. I often do this as an analogy in terms of bonds. Imagine me teaching a classroom, and one of the kids walks in, and he walks in holding a hand grenade. Now, at this point, and he pulls the pin out and throws it on the floor. And at this point, everyone's going to panic and they're going to run out of the room. Now, as he pulls the pin out and throws it in the floor, the next student walks in and he's holding a V2 rocket. He's a big guy. He walks in, V2 rocket on his shoulder, and dumps that in the middle and pulls the pin out. Now, at this point, you're comparing a grenade. Don't get me wrong, a hand grenade. Made a mess of that. A hand grenade. A hand grenade to a V2 rocket. So a hand grenade is, we know that these are tiny things, and you're now comparing it to a V2 rocket. Yeah, V2 rocket, which are massive things. They're 5 stories higher. Well done, Harry. Thank you for contributing. Appreciate it. And at this point, what disappears from your mind is the hand grenade. You don't care at all about the hand grenade. Because all of a sudden, it's not about getting out of the room, it's about getting out of the building. because the bigger bomb is what matters. And in this scenario, the ones that matter are the stronger ones, the HBs and the DDs. Yeah. Now, at this point, a third student walks into the classroom, and he walks in with an atom bomb on his shoulder, and he places that in the middle of the room. And at that point, the thoughts of the V2 rocket completely disappear out the window. It's now not about getting out the building, it's about getting out of the city. Yeah, the strongest of the forces means that the only one that matters is usually the one that's strongest. And they love this. Identify the strongest weak intermolecular force. It's a very common question at exams. So, okay, at this point, we can predict the melting points. HF is going to be the highest melting point. In terms of MPT, melting point, this one's going to be the highest. But the question is now, what about these two? Because at this point, we know that this one's going to be the highest because it has a much stronger weak intermolecular force as hydrogen bonding. But now the question is, what about these two? The DDs are the same. Now what that means is if they are both DDs, their melting points should be the same because they both have it. But now we realize that the LDFs are going to vary. So we can now make a prediction that this one is going to be the middle value and this one is going to be the lowest. And the reason being is now not the DDs, but in fact, the comparisons of the LDFs. I know this is complicated, and after a while, it's all about the exam questions. The more you do, the better the understanding of this becomes. You start to realize when you need to look at certain forces, when you look at others. And we can now check this. So the boiling point of HF, now this is where I'm not going to get this wrong. Hydrogen fluoride boiling point. Boiling point 20 degrees Celsius plus 20 degrees C. Right, HCl. I've already done this one. Minus 80. HCl. Hydrogen chloride minus 85. 5 degrees C. So what about HBr? It should be higher than HCl because the molecule is larger. Bromide. So it should have stronger LDFs. But got to be careful. Boiling point 66. Minus 66. It's bigger. So the graph now looks like this. Plus 20, minus 85, minus 66. And we can now predict where would HI be versus HI. We can now predict this. Once again, it is a DD. But these all have DDs. We now need to compare the size of the LDFs in order to recognize their boiling points. And it's a bigger molecule, so it should get stronger. So if we now go to hydrogen iodide, we now get a boiling point. I've put them as melting points, and I shouldn't have. Oh, hydrogen iodide has a boiling point of minus 35. They're increasing. Yeah, there we go. We can even find a graph for these. Hydrogen halide, boiling points, images, and we get a nice, beautiful graph showing the trend. So they go down and then they go back up as the LDFs increase in strength. Next, so that actually brings us to the end of intermolecular forces. Now, I am incredibly aware that we need to create some form of a summary. So, summary of LDFs. Number one, we need to know the description. Yeah, electrons are in motion, so they form temporary dipoles, which induce dipoles, and then neighboring, there's an attraction between the temporary and induced dipole. We're done. Why they build up. The bigger the MR, the larger the number of electrons, the stronger the LDFs, and you're done. That's all we need as a summary. I'm going to end my lesson there today. Next lesson, I'm very aware that I'm taking this incredibly slowly, which is not a good thing. I'm very much behind. But next lesson, I'm going to focus on exam style questions. I'm going to post you your homework. Your homework is going to be exam style questions on this, so you can start putting this into practice. and then I will talk you through in the next lesson. Guys, go and have a nice rest of your day, and I'll see you all soon. See you later, guys.